All right, so we last finished and we were talking about chirality. And we said in order for something to have chirality, you have to have a carbon atom, and that carbon atom has to have four different groups bonded to it. And that's what we would consider a chiral carbon. So if any molecule has a carbon with chirality, then that molecule has a mirror image, has an enantiomer, right? And we talked about enantiomers last time, but we're going to go over all the definitions again, right? So the non-superimposable mirror image molecules, those are the enantiomers, which is a subset of stereoisomers, right? Okay, so if you talk about glyceraldehyde, it's the simplest sugar, which I'm going to show you in just a second, that has a chiral carbon. And a lot of times you have big molecules, and those big molecules have lots of carbons. So the more chiral carbons you have, the more number of different isomers you can have. So here's glyceraldehyde. Glyceraldehyde has one chiral carbon. So if we look at glyceraldehyde, we're going to find the most oxidized end, and that's always the end that has the carbonyl in it. And we're going to give that carbon number 1, carbon number 2, and carbon number 3. So what I want to do is I want to look at each of the carbons inside of my glyceraldehyde and determine how many are chiral. So if I look here at carbon number 1, it has 1, 2, 3 different things attached to it. So it can't be chiral because it doesn't have 4 different things attached to it. I go to carbon 2. If I go up, it's a carbon and a carbonyl with a hydrogen. If I go down, it's a carbon with a hydroxyl. So those are 2 different things. Then it also has a hydrogen and it has a hydroxyl. So that's 1, 2, 3, 4 different things that surround that carbon number 2. So carbon number 2 is chiral. So a lot of times they'll do a little asterisk. But in a Fisher diagram, if you have a carbon, and I'll show you it in just a minute, so that you can kind of see how they do it. But a lot of times when we draw, this is called Fisher diagrams. You would draw a carbon, and then you would just draw something like this. And anywhere where you would have a plus sign, so I'll finish the molecule off here, H, O, and H. Anywhere where you would have right here at the center a plus sign, that would just be a chiral carbon. So sometimes you do it with an asterisk, and sometimes you do it to where it's almost like a skeletal diagram, but it's not a skeletal diagram. But all right, and then if I go down to carbon number 3, what I see with carbon, see if I can do this again. Okay, what I see with carbon 3 is that carbon 3 has 2 hydrogens attached to it. So even though it has 4 different things, it has 4 things, 2 of those things are the same. So then it is achiral. So the only chiral carbon in this entire molecule is this one right here. Okay, so if I look at the last chiral carbon, so if you want to know if something is D or L, we talked about this last time, you look at the last chiral carbon. Okay, so you have to always number correctly. So you have to number your most oxidized. So my highest numbered chiral carbon is carbon number 2. So if I look at these 2 molecules, these are both diglyceraldehyde. If I look here, I have the hydroxyl on the right. If I look at the other one, I have the hydroxyl on the left. And so these are non-superimposable mirror images. So they are enantiomers, and we have the D and we have the L. So the D is on the right, the hydroxyl. So you look at the last chiral carbon, so it's D or L. You look at the last chiral carbon. If OH is on the right, we call it D. If OH is on the left, we call it L. So like your left hand and your right hand, L is left, and D is right. Okay. And we talked about we talked about this with the different molecules. Remember that we had 4 different things attached to them, but instead of being, carbons, they were just like a purple one or a blue one or whatever it is. And so what you have to look at is these are non-superimposable mirror images. So if this were a mirror, you would actually would look like the same thing, right? But it's not. We know we can't superimpose them. And so we did that in class. All right. So the way that we know that things are enantiomers is that they are optical isomers. So they interact with polarized light in different ways, and they actually rotate how the light works. So this is called optical activity, and you don't really have to understand it. It's okay. The book goes through how it all happens. I'm not worried about that. I would much prefer you understand the Fisher diagrams and everything like that. So when we talk about our sugars, you're going to see, this is what I alluded to earlier, Fisher projections of the different molecules. So if we kind of zoom in, right, we're saying that this one is a hydrogen, this is a chlorine, this is a fluorine, this is a bromine. So what we do is that we, a lot of times to try to show 3 dimensions, we use dashes and wedges. So we know that if something is going out of the page or going into the page, then it's going to have either a dash or a wedge. But gosh, that takes a really long time, right? So just like I was showing you, anytime you have a chiral carbon, like this carbon is chiral, so I could put the little asterisk, I see it's 4 different things attached to it, or I could just draw it in that simple plus sign the way that we drew it on the page. And so it tells me that it's chiral, but there's a little bit of other information that's in this drawing. If you are looking at things that are going left to right things are oriented toward you, just like the solid triangles here, the wedges, right? And then if you had something that goes up and down, this is implying that it is going away from you, away from the screen, just like all of these dashes indicate, right? It's the same thing. These 2 mean the same thing. So even though it's drawn in 2 dimensions, it's giving you a bit of 3-dimensional information, right? So, and it's a lot easier to draw the Fisher diagram than it is to draw the wedges and dashes. But, okay. So let's look at some sugars. Remember, your most oxidized carbon is always going to be at the top, always going to be carbon number 1. And so remember, when the book is showing you this CHO, what can you do? You could go in and you could get rid of the O and the H, and we could draw it like it's really supposed to be, right? We know what it's supposed to be. We know that that's a carbonyl, right? And then a hydrogen, okay? So anywhere where you see the CHO, you know that that's has to be a carbonyl, and so that's the most oxidized, so it gets number 1, right? If we look at something a little more complex, we're going to look at glucose. Okay, if I number it, I say, okay, I have, my first carbon is achiral, but every carbon after that, 2, 3, 4, and 5, these are all chiral. And then I get down to C6, and C6 is achiral. So I don't show it as the Fisher line cross. We just draw the C so that we know automatically how many carbons are chiral in this molecule. There are only 4 carbons, 2, 3, 4, and 5. So then the question is this D or is this L? So all I have to do is find the last chiral carbon, which would be carbon number 5. Look at the hydroxyl. The hydroxyl is on the right. So it is D-glucose. And you should know the structure of D-glucose. Like, you should know where the hydrogens versus the hydroxyls are on the Fisher projections. This is one thing you should know. You really do need to know your structure for D-glucose. If we were to look at D-fructose, what we can see is we're going to give our oxidized carbon the lowest number possible. That's carbon number 2, because we have to do our longest continuous chain. The carbon that's above my carbonyl would have to get carbon number 1. So just make sure that you try to give that carbonyl carbon the lowest number possible, but you make sure to number it just like we've numbered in the past, where you give it that longest continuous chain. But carbon number 2 is achiral. So see how it's not a perfect plus? That's another indicator that it's achiral. It has to be a perfect plus sign. So carbon number 3 is chiral, carbon number 4, carbon number 5. We get to carbon number 6, that's achiral. So this molecule that we're looking at right now is D-fructose. And D-fructose has only 3 chiral carbons. And we know it is D because we look at carbon number 5, that's our farthest carbon, chiral carbon. And we look at the hydroxyl's on the right. That makes it D-fructose. And you're seeing all these D's because that's what our body metabolizes. Our body metabolizes things that are in the D form. So when we talk about compounds that have chiral centers, a lot of times you can end up with what's called a racemic mixture. And it's a mixture where we have both D and we have L enantiomers, right? Sometimes they call it a racemake, but half of it polarizes light in one direction, half does the other. So they call it optically inactive. And so sometimes they'll use the plus minus as an abbreviation because you have a positive rotation and a negative rotation and it cancels out. So, but I don't care that you understand about the light. Diastereomers, you can have diastereomers. Remember, diastereomers, these are not mirror images, but they are arranged differently. So it's a pair of stereoisomers that have 2 or more chiral centers that are swapped. And I'll show you what that means in a minute. But they're not enantiomers. They're not perfect mirror images. And I'm going to show you some examples in just a bit. Okay, then you can have, so that's diastereomers. Then you can have meso compounds. Meso compounds have to have 2 or more chiral carbons and an internal plane of symmetry, which is really kind of weird. And I'm going to show you what that is below. Okay, so let's look at these different sugars that I've drawn, right? Well, and we'll number our carbons. We'll go 1, 2, 3, and 4 carbons. Okay, so if I look at A and B, when I compare the two, I'm looking and I'm going, okay, I have 2 chiral carbons. And if I look at this, okay, my 2, if I get to carbon 2, this is 1, 2, 3, 4. If I look at carbon number 2 on A, and I look at carbon number 2 on B, what I can see is the hydrogen and the hydroxyl are swapped to get from A to B. Okay, same thing when I get to carbon number 3. I look for the hydrogen and the hydroxyl, and I see they're swapped. So if I took carbon number 3 and I swapped the hydrogen and the hydroxyl, I would end up with molecule B, right? So how do I name this? If I put a mirror right here, would it be a non-superimposable mirror image? Yes, it would. It would be a mirror image. So we call these enantiomers, non-superimposable mirror images. Now, if I look at C and D are really similar, right? And I would think, okay, let me number my carbons. 1, 2, 3, 4. 1, 2, 3, and 4. Okay, and I would think, okay, if I drew myself a mirror right down the middle, it would be a non-superimposable mirror image. And that's true, but what if I took this molecule, see if I can do this, and I take it and I rotate it, and I'm changing the size, and I rotate it. Look at this, it's gonna match perfectly. And that's because this has an internal symmetry. So if I drew a line right here and right here, the top is exactly the same as the bottom. So we call these meso compounds. They're identical mirror images. So we call them meso compounds, because that internal symmetry allows you to just rotate it 180 degrees and it's the same molecule. So, okay. Now, oh, and that was if I messed it up, I was going to be able to rotate it again. All right. So when we talk about our sugars, right, you have to be able to draw them in Fisher production. You have to know where to start your numbering. So always with the most oxidized species, which is typically the carbonyl, the closest to the top that you can get it. Either it's really either going to be 1 or number 2, basically. Then if you want to know if it's D or L, so this is D or L. If the chiral carbon with the highest number, so this is the farthest chiral carbon from the carbonyl. If the OH is on the right, it's a D. If the OH is on the left, it's an L. Most of the sugars, like we said earlier, are in the D form. And that's because our enzymes are not designed to handle the D form and D form only. So if we look at these different molecules, right? If you give your most oxidized carbon, that's the one in the carbonyl 1, 2, 3. And in this case, the only chiral carbon is the one that's there. So this is on the right. And so you can either do it with dashes and wedges, or you can do it in the Fisher diagram. Regardless, it's still on the right, which makes it D-glyceraldehyde. On the other hand, if we have the hydroxyl on the left, that tells us it is L-glyceraldehyde. 2, 3. This is 1, 2, 3. Okay, so what we really need to talk about are the biological monosaccharides, the ones that we are going to use in the body all the time. So glucose is really the most important sugar in the human body. Yes, we eat it, and we eat things that break down into glucose, and we name them very, very different things. Sometimes you call it dextrose. So if you're looking at giving someone whose blood sugar is really low, you might give them D5W, so that's dextrose. But regardless, it's the same thing. So how does the body regulate it? It regulates it through insulin and glucagon. Your body secretes insulin when you have high blood sugar, and your body secretes glucagon when you have low blood sugar. So in the body, in physiological conditions, glucose is going to convert from that straight chain into a cyclic molecule. And in order for that to happen, it's going to turn into a hemiacetal. And you remember what an acetal is, and I'm going to remind you. But the hemiacetal is going to form where your C5 hydroxyl, this is really important, your C5 hydroxyl reacts with the C1 carbonyl group. And I'm going to show you this in a drawing in just a second. Because of the way this forms, there are 2 different isomers that once it's cyclic can exist. And it all depends on the location of the hydroxyl on the acetal carbon. So I'm going to show you some drawings. So we're going to talk about this. So if you have, this is just kind of a reminder to tell you what a hemiacetal is. If you start with something that's an aldehyde, and remember when we talked about sugars, sugars are either ketones or aldehydes. And this could also be true of a ketone, but you would have an R2 here instead of an H. So, you know. All right. So here we're starting with an aldehyde. And our oxygen on our alcohol and this is going to be an intermolecular. I'm showing you this as two different molecules because this is what we did in the past. We said we had an aldehyde and we had an alcohol. And the carbon is going to make a bond with the oxygen in the alcohol. The alcohol is going to give up its hydrogen to the oxygen that was in the carbonyl. Because remember, when one of these bonds is gone, the oxygen's not happy and the carbon's not happy. So each of them need to pick up one additional bond. The carbon is going to bond to the oxygen in the alcohol, and then the oxygen is going to pick up the hydrogen. And so once that happens, and I totally did that wrong, that's supposed to be an oxygen there. I think it's a different color blue. Yeah. Okay. An oxygen there, and then we're going to pick up that hydrogen right there. And so now we have a hemiacetal where we have an OR and an OH group. Okay, so make sure you fix that in the little handout that I gave you. So remember your definitions. If you're a hemiacetal, you have one OR group and one OH group. And that's what we have, one OR group and one OH group. If you were a full acetal, you would have those two OR groups. But that's not what we have. We have a hemiacetal. Okay, so why does this matter for glucose? Well, this is exactly what happens when glucose turns into a cyclic molecule. And when we turn it into a cyclic molecule, we call this a Haworth projection. And so I'm going to show you exactly what can happen. So remember how we said we needed something that was an aldehyde, and we need something that is a hydroxyl. And that's exactly what we have. And so remember what's going to happen. What's going to happen is this molecule is basically going to bend this way and this way, right? And so this is exactly the same molecule drawn, except it's not in a straight line. It's now curved around. So remember what's going to happen is one of these double bonds is going to get lost, right? So let's draw over them in white. Let's do that. So come on. Okay, so we're going to lose that double, one of the bonds in the double bond. Now, the carbon and the oxygen need to pick something up. So what's going to happen is we're going to form a bond between the carbon and the oxygen. And then this hydrogen right here is going to go and bond to this oxygen. And it looks really far away, but it's in real life, it's not, right? So what ends up happening is you're going to finish this ring. So where the blue line is, it's just a bond. So, and this is an oxygen and this is a carbon. So basically you're going to have a ring, right? You see this ring that's all carbons, except right here, we have an oxygen. So you're going to end up with a ring structure with an oxygen in one of them. And then this hydroxyl is now going to be like sticking out. And so there are two different ways that that hydroxyl can stick out. So remember when we talked about these Fisher diagrams being, one's coming towards you, one's going away from you, and all that kind of stuff. You have to remember that when you turn it into a Fisher diagram, you're doing the exact same thing. So when we look at if something was on the, here, if something is on this side of the molecule, so we're on the right, so everything that was on the right, so groups on the right, those are the ones that are going to end up being down. So we'll go down. The ones that are here are going to be the ones that end up going up. So this is groups on the left go up. Okay, so if I look at my Haworth projection, you have to kind of think about, okay, where was the carbonyl carbon? Because we still want to give that carbonyl carbon the lowest number possible. And so when we look at the ring structure, the way that you find your carbonyl carbon, and I'm going to write this on the side. So what was the carbonyl carbon is now, had, of course, a new name, is now the anomeric, anomeric carbon. So the anomeric carbon is a carbon bonded to two oxygens. So if I look here, this carbon right here is bonded to one oxygen in the hydroxyl and one oxygen in the ring. So what was the carbonyl carbon, now this one is the anomeric carbon. And so you want to give the anomeric carbon the lowest number possible. It's still the same carbon. And so we need to name it the same way. So now we're going to look and say, okay, well, if number 1 is the anomeric carbon, I'm going to go to number 2. And I need to know, is my hydroxyl on number 2 going to go up or is it going to go down? Well, if it was on the right, it goes down. Go to carbon number 3. If it's on the left, it goes up. Go to carbon number 4. If it's on the right, it goes down. Carbon number 5. Now here's the weird thing with carbon number 5. Carbon number 5, this oxygen right here is this oxygen right here. So you're not looking to put a hydroxyl on carbon number 5. Carbon number 5's group is a hydrogen and this CH2OH group. The oxygen you've already drawn because it's in the ring. So you really only have to worry about the hydrogen and then the CH2OH group. So the standard in the field is to put the C2OH up. So this will always be drawn up, which means it's above the ring, right? Up means above the ring, down means below the ring, because it's a ring structure. So if we do it that way every time, the only thing that we still have to worry about is on carbon number 1, what's going to happen to the hydroxyl that's on carbon number 1? That's this hydroxyl right here. Does he go up? Does he go down? Well, either one can happen. Sometimes it'll go down, sometimes it'll go up. It actually happens a little bit more where it goes up, but it doesn't really matter because both happen in the body. So we have to have a way to show this. So because if we always draw carbon number 6 going up and outside of the ring, then all we have to do is look at the comparison of the two. If they are both up, it's just like saying cis, but because it's a ring, we don't say cis anymore, we say beta. Here, I'm showing carbon number 6 going up. I'm showing the hydroxyl and the anomeric carbon going down. So up and down is used to be called trans. Now it's not called trans anymore. It's called alpha. And it's kind of like that A with a loop on the top and the bottom, but it's alpha. This is beta, right? And it's just like cis and trans, but we don't say cis and trans because it's a ring. Okay. All right. So now I kind of want to reiterate a few things. And I think having kind of a color drawing really helps. So if we start out with a Fisher diagram, we need to be able to go over to a Hayworth projection where we're looking at the ring structure. And so remember how we said anything that you have on this side of the molecule, right? If it's on the right, what's going to happen to it? It's going to go down. If it's on the left, it's going to go up. And then remember, we don't really worry when we get to that last chiral carbon. We don't worry about what's going to be up and what's going to be down, because the oxygen here is going to make a bond, and that's this green line, with the carbon all the way up here. So you're not really going to have a hydroxyl to worry about there. But you will have this hydroxyl, excuse me, that you're going to have to worry about. So we'll get to that in just a second. So when you get to carbon number 5, you need to worry about making sure that this goes up. Okay. So when we went and we go ahead and draw it, so my suggestion is to like hide it and actually try to draw it. So we're on carbon number 1, and I'm not showing the up down because that's alpha or beta. And so I'm not showing that. I want you to see everything else. I look at carbon number 1, and I'm going to draw however many carbons. If I have a 6 carbon chain, that means I have 6 things in the ring. One of the things in the ring is an oxygen. So that means one of the carbons is going to be outside of the ring. So kind of be careful on that and count. So what was your carbonyl carbon? So this is the carbonyl carbon. Because really, what does this HO here mean? It means we have a double bond O and we have a hydrogen, right? Okay. So what was the carbonyl carbon now becomes the anomeric carbon. ER, that's an I, ERI. It's kind of like overlapping here. Anomeric carbon, okay? All right. So our anomeric carbon is bonded to, if we go this way, 1 oxygen, we go this way, another oxygen. So our anomeric carbon is always bonded to 2 oxygens. We try to give that carbonyl carbon the lowest number possible. So if I had a carbon, like if I had something like CH2OH here, this would get carbon number 1, that would get carbon number 2. But that's not what we have here for glucose. Okay. So then we go around the ring and we number. So the next carbon, carbon number 2, we look at carbon number 2 over here and we say OH is going to the right, so it goes down. Hydrogen's on the left, it goes up. And you go through and you do that for all of your carbons until your very last one. Your very last one, carbon number 5, you put this CH2OH going up. And then that allows you to have the position of the hydroxyl and the anomeric carbon determine if it's alpha or beta. So we call the Fisher diagram, this is just D-glucose. When we put it in the cyclic form, sometimes you'll hear it called glucopyranose. Pyranose is another way to say cyclic. Okay, so now I want to review some of these terms when we talked about if you had chiral carbons, and some of them had different stereoisomers and that kind of thing. So I want to show you a few things. So you can have D and L, right? So D and L, all we're saying is that we have perfect mirror images of one another. So on the left, all the way over here, let me see if I can use this. This is D-glucose, this is L-glucose. So if I were to put a mirror between the two of them, I should have mirror images. So the way that I check that is I look at carbon number 1, as long as the same letters are there, the same elements are there, it's good because that carbon is not chiral. So if we go to number 2, look at number 2. Do you see how the hydrogen and the hydroxyl are flipped? So carbon number 2 is flipped. Look at carbon number 3. 3 is flipped. 4 is flipped. And by flipped, I just mean that hydrogen's on the left here, it's on the right here. Hydroxyl's on the right here, it's on the left here. So they're flipped. Look at carbon number 5. Here I have my hydroxyl on the right. Here my hydroxyl's on the left. And so if I look at these, they're non-superimposable mirror images. All the chiral centers are different. So therefore we call it an enantiomer. Okay. Now, if I compare D-glucose to L-idose, so I'm going to do the same thing. I number my carbons. Then I'm going to look at each of the chiral carbons and I'm going to ask, are they the same or different? So if I look at carbon number 2, oh, carbon number 2 is the same, right? Hydrogen on the left, hydrogen on the left, hydroxyl on the right, hydroxyl on the right. So carbon number 2 is the same. Okay, carbon number 3, oh, same. So carbon number 2 is the same. I'm sorry, carbon number 3 is the same. Okay, let me erase some of the lines. All right, then I go to carbon number 4, same. This is looking like the same molecule, but I don't think it's the same molecule. Okay, so this is same. All right, now when I get to my last chiral carbon, I look here, hydrogen's on the left, here hydrogen's on the right. So this is flipped. So if you have one or more chiral centers that are flipped, we call those diastereomers. So diastereomers, they're isomers, but they're not superimposable mirror images. If you only have one chiral center that is flipped, we call those epimers. So you could either call D-glucose and L-idose diastereomers, or you could call them C5 epimers. It's the same, it's telling you the same thing. Okay, so now if we compare L-iodose to L-glucose, so I'm going to do the same thing. I'm going to look at carbon 2 and I'm going to go hydroxyl on the left. Oh, hydroxyl's on the right. Okay, so this one is flipped. Okay, so I look at the next one and I go, whoa, look at this. Okay, I got hydrogen on the left, I got hydrogen on the right. So this one's flipped. Same thing, this one's flipped. And when I get to my last one, oh, it's the same, right? So this is 3 of my 4 chiral centers are flipped. This one's the same. So those, again, are diastereomers. So they're diastereomers if they're not mirror images. So here, has 2 or more chiral centers and are not enantiomers, not mirror images. Enantiomers are those D and L. They differ because they're non-superimposable mirror images. So all the hydrogens and hydroxyls are swapped on chiral carbons. And that's what makes it an enantiomer. Okay, so just go through and check that. And then epimers, we said, have 2 or more chiral centers, and then at least one, it's only one chiral center that's different. So you can tell if things are diastereomers or enantiomers when they're also in the pyranose form. So remember how we said if something was on the left, it goes up. If something's on the right, it goes down. So all you have to do is look at ups and downs, and you could do the same thing. So you can look at D-glucopyranose and D-iodopyranose. So it's just the cyclic forms. And you could say, I'm going to look at each of the chiral carbons. So I'm going to start with chiral carbon number 2, right? And I'm going to look and I'm going to say hydrogen's up, hydrogen's up. So that's the same. Carbon 3, hydroxyl up, hydroxyl up. That's the same. Carbon 4, hydrogen up, hydrogen up. Oh, when we get to carbon 6, now we have it swapped. So this is our way to see that we have a diastereomer. It's not an enantiomer, it's a diastereomer because I have that one chiral center that's swapped. It's not all of them, it's just one. So then if I look at, let's say, D-glucopyranose versus L-glucopyranose, all I have to do is look, okay, here's 2, right? And I have hydroxyl up, oh, hydroxyl down. So that's swapped. 3, I have hydrogen up, oh, hydrogen down, that's swapped. Hydrogen down, hydroxyl down, that's swapped. And then C6, CH2OH is down, CH2OH is up. So now everything is swapped. So that gives us the D and the L. Those are the enantiomers. And then I'm not showing this hydroxyl here being up or down. So I'm not able to say anything about alpha or beta, but you could get that information, but I'm just not giving it to you here. Okay. And then I think we'll pick up on the rest of it, let's see how much farther we got to go. I think we'll pick up on the rest of it in class next time. All right. Y'all have a good day.